In this video, I will explain two different ways to integrate the function secant. Specifically, this is the calculation I want to do. This problem was historically very important. In the early years of calculus in the 17th century, in the field of cartography, it was necessary to actually perform this integral analytically. And mathematicians struggled for a while to solve the problem, because there is no apparent easy answer. I'm going to explain two solutions to it. The first one is the method that appears in all calculus textbooks. It's fast and simple, and I don't like it. I will explain why, and then I will propose an alternative method. For my first method, to integrate the function secant, I'm going to start by multiplying and dividing by secant plus tangent. Why? Hold on to that question. Okay, and now that I have it here, I'm going to try a substitution. The substitution I will try is u equals secant of x plus tangent of x. You may wonder why I try that. Again, hold on to that question. I'll come back to it. If I use the substitution, then the differential will be the derivative of secant is secant tangent, and the derivative of tangent is secant squared. And now, look at what happened. This expression here is exactly what I have at the top. What are the odds? So that means that the integral becomes du at the top and u at the bottom. And now I can complete it from here. This antiderivative is logarithm of the absolute value of u plus c, or, after I'm doing the substitution, logarithm of the absolute value of secant plus tangent plus c. And we are done. This is the method that is presented in almost all calculus textbooks. And the method on itself is easy to understand. Once I explain it, it is clear why it works. And in particular, it is very simple to check that the answer is correct by taking this function, computing its derivative, seeing that it equals to secant. But of course, this leads to the question, why? How on earth did we think of this? How did anybody think of trying this substitution in the first place? And more importantly, how did somebody come up with the idea of multiplying and dividing by secant plus tangent? This seems like too much of a leap that one has to take. And I don't have a good answer for that. I don't know how to explain that this is something you should have thought of, because I would have never thought of it myself. And that is why I'm going to propose an alternative method. So my second method is going to be longer, but I think it's more natural in the sense that an average student with enough practice integration could have come up with it. For the second method, I'm going to first rewrite secant as 1 over cosine. And now I am going to think of this as cosine of x to the power of minus 1. And I'm doing that because this reminds me, this is an aside, of this family of functions. We know there is a general method that allows me to integrate any function of the form a power of sine times a power of cosine. And, well, this is the power of sine times the power of cosine with exponents 0 and minus 1. And in particular, I know that when I have a function of this form and the exponent of cosine is odd, then there is a substitution that helps. And that substitution is u equals sine of x. Okay, so motivated by that, by how this family of functions works, I'm going to try the substitution. If I want to do that, I need the differential, which is cosine of x dx. So I'm going to start by putting a cosine in the numerator, so I have it ready for the differential. And now, in order to be able to complete this substitution, I need to transform the rest of the cosines into sines. But I can do that because I have cosine squared. Okay, and now this is ready for integration. That is what I need there. So let's perform the integration. And I'll pause here. I'm going to call this progress. I have transformed this integral into this integral, and I think this one is easier. Well, I didn't know how to do this one. This is a rational function. This is a quotient of polynomial. That's an important family of functions we need to know how to integrate. And there is a method for integrating any rational function, any quotient of polynomials, by using partial fraction decomposition. So perhaps you haven't learned that method yet. And that's, I'm not going to finish it. I'm going to stop here, and I'm going to say, learn the method to integrate any quotient of polynomials. And once you have done that, then come back here and complete this problem. So as I said, this method is longer than the previous one, but I think it is more natural. I think the two things I have to do in the process are natural things that one can think of, and that is why I prefer it.